welcome to the class of real analysis. This part of video it is just for the discussion of the topic on series. Topic on series. First of all, just to clarify what is series. In a very simple way, you should consider series as sum of sequence. So a quick review for the sum notation, sigma notation here. It has a lower bound and upper bound with increment p there. So the summation notation simply means we are adding the terms from n all the way up to n plus p. And in particular, we do have the sum notation or sigma notation. We're counting the lower term from 1 all the way to n. And indeed, if you remember, this is so-called partial sum. Okay, and partial sum notation. And now, after knowing the partial sum notation, we can say precisely what we mean by the convergence or divergence of series. Keep in mind the partial sums, okay, the terms of partial sums indeed turn out to be sequence, right? So like we discussed before, we know how to say precisely for the partial sums convergent or not. So when now we say the series converges if the sequence of the partial sum converges. And then certainly if the series is not convergent, we say the series diverges, convergence or divergence. Okay. It's really based on partial sum. And especially, I got a few examples. I suppose these are relatively simple examples. The first example, it is a series. It's just the sum notation, sum of starting from, let me try to see if I can get this correctly. We are adding numbers like -1, then 1, and -1. Well, it's a little harder for me to fix things right now. Just put it in this fashion. Yeah, this will work. -1 plus 1, and -1 plus 1, and then -1 plus 1. Things going like that forever, right? And then one possible way of thinking the series, because we know the so-called commutative property or associative property for addition. So possibly we can think about making a series arrangement like this, getting -1 and 1 paired together. That's a 0. And then -1 plus 1 paired together. And indeed, we can continue pair those numbers together. This is a very simple way of thinking, okay? You see, if you are convinced such arrangement would work, looks like in the end we're going to have 0. But the question is if the series is really 0 or not. Okay, it's questionable. I say it is questionable because I just figure out, looking at the same series, if those ordinary commutative property or associative property holds, possibly I can make another kind of arrangement. I would just leave the first -1 untouched. Then I have 1, -1 paired. And then I will have 1 and a -1 paired. And this could go on forever, right? And then I say possibly, I could make the same argument such that all those paired elements together are just zeros. But there is something unusual. I left this -1 in the very front, untouched. So if that is the case, we're going to have this -1, right? You may want to say, wait, a limit. When we say limit, there's only one limit, cannot be 2. So indeed, the answer, it is divergent. It is divergent. Such a series is divergent. So I hope you can convince yourself using the concept of partial sum. The series, it is indeed divergent. Okay. And also I listed another two very common types of series, geometric series and the so-called P series, right? Geometric series is convergent if the absolute value of the common ratio it is positive. It's the absolute value of the common ratio it is positive, and then it converges to b is the first term, r is the common ratio, b over 1 minus r, the geometric series. And another series I listed here, it's the p series. Remember p equals 1, it's a harmonic series, and the harmonic series divergent. P equals 2, we are adding the square, the reciprocal of the squares of positive integers all together. And indeed, we did have the actual sum for that case. Turned out to be pi squared over 6. Quite interesting, right? Adding those perfect squares all together, in the end, we got something about a pi there. And also it's worth to mention not only we have the formula for 1 over n squared, indeed, there are formulas for sum of squares, and even with p, not only squared, could be to the fourth power, or I think all the even number powers. But I think you can do a Google search, internet search, or ask for AI if you can find a formula to something like 1 over n cubed or something like that. And it's kind of interesting thing. But for our purpose, we don't really need to know the actual sum. We are just looking for the convergence or divergence of the series. Okay, two common types of series, geometric series, P series. And then in general, we may have series not just a geometric or P series. So this is the general criteria you may want to consider. Cauchy's criterion. Okay, it simply says a series is convergent if and only if for any epsilon greater than 0, there exists some n, uppercase n, so that for any lowercase n, which is greater than the uppercase n, and for some p greater than or equal to 0. Okay, and such a sum starting from n all the way to n plus p, it is less than epsilon, and that is the Cauchy's criterion. And if the Cauchy's criterion is true, and then we say the series is convergent. For sure, it is convergent. And also one particular thing, this is a more Cauchy's criterion. It is a more generalized situation. And then if you look at the next part of the theorem, we are only looking at the case when p equals 0. P equals 0, it is just the nth term, right? So which simply says, if the series converges, and then the term, okay, the limit of the term got to be 0, got to be 0, got to be 0. Or really, this is indeed the famous divergence test, which simply says if the limit of the term is not 0, the series divergent, okay, divergence test. Now let's take a look at what is about next part I have on my notes. Oh, it's more generalized discussing our alternating series. Remember the series we just talked about, 1, -1 forever? And so our alternating series, it simply means we are having well, we can consider alternating series formed in the fashion, okay, starting from the series with all positive terms, and then multiply each term by -1 to the power, and that is an alternating series. And also we have the alternating series test, which is derived from the Cauchy's criterion. And did I put any proof there? I have a little bit of proof there, and you should take a look if this line makes sense to you. I'm talking about this line. I just put the word why here because it looks like to me it should be true. And if you are following the book or if you are listening to me right now, you may want to pause a little bit. You want to take a look if this indeed the statement is true. Okay, the statement is true here. This is the alternating series test. Really, it is alternating series test. And then what I want to talk about here is, well, actually, maybe still let's mention this part of result somewhat. It is important. For a series with non-negative terms, it is convergent if and only if the partial sums form a bounded sequence. Forms a bounded partial sum forms a bounded sequence. Okay, forms a bounded sequence. And, then another big thing you may want to know about the convergence of series. Somewhat we have a better kind or stronger version of convergence for series, the so-called absolute convergence. Concept-wise, it should be easier to follow. If the series formed by the absolute value of the terms of series and converges, then we say the series converges absolutely. As a simple example, remember the P series. P equals 1. It is a harmonic series. It is divergent. But if you consider the corresponding alternating harmonic series, it just turns to be convergent. So overall, the series, the alternating harmonic series converges, but not absolutely. And when p equals 2, again, it's a p series. P equals 2. We know p equals 2, the series is convergent. And also, when you consider the corresponding alternating series, when p equals 2, it converges too. It converges too, because it does meet the requirement for the alternating series we just talked earlier. Okay, this is the alternating series test. So for P series, when P equals 2, it converges absolutely. It converges absolutely. Okay. This is just the introduction part of the series. Hopefully, a lot of material. It is just same what we have done as undergraduates. Okay. So we'll have a little more. So I'm not, well, I really don't this kind of video a lot. I don't think I want to make a long video. Besides, I don't think I only have a free account with YouTube. I don't think YouTube will let me make some long videos. So how about before we move on to the comparison task, let's take a break. Thank you for watching.